Hi, I'm Mo Liu. It's my pleasure to present my research on pricing under the generalized Markov chain trace model, learning through large-scale click behaviors. So let me start with one example. Suppose I'm going to buy a shirt on a website, and there are 5 shirts to be selected. Then my clicking behavior can be the following. First, I randomly choose the shirt to click on, let's say number 3. If I like it, I buy it immediately. If not, I have 2 options. I can leave the website without any purchase, or I can continue exploring other shirts on this website. If I like short sleeves, I may click on number 1 and number 2. If I prefer long sleeves, I may click on number 4 and number 5. After several clicks, I will make my final purchase decision. So the sequence of clicks before the final decision is called click trajectories. They reveal search and comparison behaviors and have more information than the click-through rate on a single product. However, they are random and contain potential back and forth transitions. So our research studied how to use click behavior to learn the preference of customers. Specifically, how to model these random click trajectories and consider the effect of assortment. Following this question, we studied how to use click behaviors to determine the optimal prices. Because the pricing decision involves the purchase behavior of customers, we need a trace model. So we adopt this generalized Markov chain trace model, which were proposed in these 2 papers, independent of the click behavior. In this model, each state represents a product, and state 0 is the no-purchase state. The transition process is as follows. If the current state is outside the assortment, we keep transitioning. If the current state is within the assortment, we purchase it with probability mu. So there are 3 types of parameters: the transition matrix, arrival probability, and the instant purchase probability mu, which is a function of price, assortment, and product. Because this trace model is independent of click behaviors, so how to connect click behavior with this trace model? In our research, we assume each state represents a product, and we add state 0 as the no-purchase state. However, here comes an issue when considering assortments, because only products within the assortment can be clicked or purchased. So we propose this assortment-dependent click model. Theta S is the click transition matrix, and the rho is the state transition matrix. We assume they satisfy this equation. This relation can be justified in 2 ways. First, it can be reduced to a trace probability in an MNL model. Second, it can be viewed as a conditional probability. We further assume instant purchase probability mu satisfy this exponential form, where alpha I is the price elasticity for product I. We are the first to model the click behavior using a Markov chain trace model. It enables us to estimate parameters using the click data. Compared to the estimation method only using the purchase data, using additional click data can have smaller prediction errors and better pricing decisions. So here are the results from the real-world data. The left figure demonstrates using additional click data can have a smaller prediction error on the purchase behavior. The right figure shows that using additional click data can have a higher revenue of the pricing decision. In practice, when estimating the parameters, we face the scalability issue. So we assume the low-rank structure of the transition matrix. When estimating this matrix, we minimize the negative log likelihood plus the penalty of the nuclear norm of this matrix. We demonstrate this problem is restricted convex and derive an estimation error bound in the order of square root r log n, which is smaller than previous result. We also observe some interesting insight on the click model. So if a product has a higher click rate, that means it becomes more preferable. But that does not mean we need to set a higher price for this product. The change of optimal price depends on our defined optimal stationary revenue, and we provide the iterative algorithm that converge to the true optimal prices. Lastly, we studied the online pricing problem where we simultaneously do the estimation and the pricing. We observed that our click model can automatically explore, so we design an exploration-free online learning algorithm where we greedily set optimal prices to maximize the revenue at each iteration. and derive a non-asymptotic regret bound in the order of square root RNT, which is smaller than the bound without low rank structure. That's all. Thank you.